Yasin, how was the exam yesterday?
It was okay. I did like a lot of exercises, so I wasn't surprised by what he was asking. But did you saw the exam?
No. I'm not the marker this semester.
Oh, okay.
What was the question?
There was a question that you needed to use the kinetic energy and potential energy equations. So it was like a mass and a wheel, so and all connected with springs. There was another question, and we had to find G equivalent, M equivalent, and K equivalent. And there was another one with a measurement device. So we needed to use like so he gave us like a frequency and said like, can we use this device to use to calculate another frequency?
Right.
So and you had to find the percentage of error that you might have. And there was other questions as well about transferability, transmissibility.
Transmissibility.
Yeah. So we needed to we didn't had omega, and we needed to use the transmissibility equations with the transformation with R, omega over omega n to find R and then find omega, and to find like how many rads. And I think he said like transmissibility was 25%.
Right.
You need to equate it to 25. But I feel like it was a bit tricky. So I don't know. I wasn't surprised, but at the same time, it was a bit tricky because he likes playing with the units of the things, right?
Right. At least you are familiar with you're now familiar with the type of question.
Yeah.
In the final, you will see more or less the same question, the same type of question, and also you will have one Lagrange question and one measurement again.
Yeah, I think, but in the final, he will not include chapter 1, 2, 3.
As I remember, in the one of the last final, there was another measurement in the final.
Oh yeah, but maybe with another method that we'll
because
learn.
in the final, normally you will be given 6 problems. You are free to choose 5 problems from the 6.
Oh, okay.
In some semesters, it was like that. In some other semester, you have only 5 questions. You have to solve all of them. But one of the question definitely would be the Lagrange method.
The Lagrange method, because he
Right.
said he will not repeat any questions from chapter 1 to 3 because
Okay.
It was like
Maybe
kind
this,
of a final.
maybe
Yeah,
because of summer, right? Because
yeah, exactly.
Maybe.
Yeah, I don't know if
Okay.
the second part, like after chapter 3, it's easier or it gets harder. I don't know.
It is not harder, just more or less the same.
It's maybe more tedious, like with the
Just you are dealing with multi-degree of freedom system. It is not harder at all. It's just the same. The basic are the same equation of motion for several.
So I just need practice and.
Exactly right. Right.
Okay.
So today let's start with chapter 5. We already started basically, and we solved one problem, 5.2, and we are gonna solve next problem, 5.7. So determine the natural frequency of the torsional system shown here and draw the normal mode curve. So there is a torsional system which consists of 2 torsional systems like this, and so this is going to be 12 inches and this is 6 inches, and the diameter is 1 inch, and here is 3/4 inches, and also the mass moment of inertia for the right wheel is 3 pound inch second squared, and for the left spring is 5 pound inch second squared, and the shear storage modulus of this, the material are being torsioned, is G for the material, which are given as 11.5 10 to the power 6 Pascal inch squared PSI. So we are heading to find the natural frequency of the system. Basically, there are 2 disks which can independently rotate, and we are dealing basically with a 2 degree of freedom system. And you can imagine there are 2 masses attached with 2 different torsional stiffness, and we could somehow, for the sake of simplicity, simplify the 2 spring and substitute the 2 spring with 1 spring and make our calculation much simpler. So we could easily treat any torsional beam like a spring. We could calculate the corresponding stiffness when you have a torsional beam. A torsional stiffness for the left spring is Gi over L, where I is the mass moment of inertia. G is the shear modulus, which is given directly 11.5 10 to the power 6, and I is polar moment of inertia. I is a polar moment of inertia, second area moment of inertia, which is pi d to the power 4 over 32. So then you could go for pi. The left beam has a diameter 1 inch to the power 4 divided by 4, and there is a L. L is the length of the beam, which is given as 12 inches. Therefore, the torsional spring stiffness can be calculated finally as 0. Yes.
Why did you divide by 4 instead of 32?
Okay. Okay. Sorry, I made a mistake.
Oh,
thank
okay,
you
no
for your
problem.
correction.
No problem.
It's 32. Thank you. So PD to the power 4 divided by 32 exactly is going to be equal 0.0941. The unit, very important, 10 to the power 6 pound inch for 1 radian. You need to apply this amount of torque in order to rotate 1 radian. So similarly, you could easily find the left spring and the right spring. The right torsional spring similarly can be obtained 11.510 to the power 6. The length of the right beam, torsional beam, is 6 inch multiplied by P3 over 4 to the power 4 over 32, which is going to be 0.059510 to the power 6 pound inch per radian. So if I want to recap so far, we are dealing with basically 2 torsional spring which is attached together, and there are 2 discs, okay, right? So if we could simplify this system by just 1 spring, our calculation toward finding the 2 natural frequency, because we are dealing with 2 masses which can independently rotate from each other, that's why we could draw a conclusion that we are dealing with a 2 degree of freedom system. If we could come up with the equivalent stiffness or effective stiffness, our calculation toward finding natural frequency would be much simpler. So left, J left and J right. So tell me where these 2 springs you could see here, these are parallel or these are springs?
It's just confusing since they are rotating, but I would say
right. I just similar by torsional. You could imagine we have M1, a stiffness 1, a stiffness 2. You could go for a linear system like this. So these are torsional stiffness. If you could consider it as 2 linear stiffness. So if we had 2 linear spring and 2 masses, how I can simplify these 2 springs, K1 and K2?
I would go in series. So I would go like 1 over K1 plus 1 over
Right,
K2.
exactly. Because the force that will pass through these 2 springs are the same, or you could say that their corresponding deflection would be different because their stiffness are different. So for example, if the K1 is very stiff, it will only just displace like this. If K2 is very soft, it will deflect very much. So their deflection are different. That's why you could draw a conclusion that they are in a series, and for a series spring we had a specific formula, but if the deflection would be the same, you could go for parallel spring, which is not the case here. And So the two springs are in series. This just for simplification.
And,
It's not
question.
just torsion.
Um, for a torsional system, what would be a parallel thing?
It's
Like
maybe I don't know, maybe there are some here and some here, maybe, I'm not sure for it.
I mean, so it'd be like two shafts?
Maybe. It's very difficult to imagine for the torsional.
Okay, no problem.
Yes, difficult. So here you have the formula for a series spring. You can apply them. These are a spring, and so the K equivalent or effective stiffness of the two spring is K1 multiplied by K2 over K1 plus K2. So we already obtained K1 and K2. We could go for finding equivalent K, which is going to be 0.0365 multiplied by 10 to the power 6 Newton meter torque you require it in order to rotate this equivalent stiffness as 1 radian. So I can now simplify the problem, which helped me to solve with 1 K effective or equivalent. So 2 J1 and J2. So now I'm gonna calculate the natural frequency and the corresponding natural mode shape that allow me my further design and analysis for vibration behavior of the system, which lately we will design the system based on this behavior and natural frequencies. So since they so what is the first step toward calculating the natural frequency for a multi-degree of freedom system or single degree of freedom? What is the first step toward calculating the natural frequency?
Turn into matrices, I think.
Yes, we need to derive equation of motion. So omega n, we need to derive firstly as a first step 1 equation of motion. And then since we are dealing with multi-degree of freedom system, as you clearly said, we will go change it into the matrix format. So for deriving equation of motion, you could take, this is a rotational system and we have not reached the Lagrange. We have still need to go for Euler formula, which is very simple for this type of problem. I will tell you which type of problem is very difficult, but now it's very, very simple to use Euler formula to come up with equation of motion. So if you take a look at here, there are two masses. Let's focus on the let's write the equation of motion for the left torsional disk. So there is a torsional disk like J1. If I look at from this side, I will see this torsional system. So in order to basically use the Euler formula, summation of momentum around point O is JO theta double dot 1. So I assume this is going to be my positive direction. So J1 theta double dot 1. So if I rotate the left disk, what is the opposes? What kind of torque will oppose the motion? So there is a spring, right?
Yeah.
There's a spring minus K, because there's a position torque minus K equivalent or K effective. since the equivalent stiffness, torsional stiffness is attached between the left and right disc, the total torsional deflection will be depend on the rotation of the two discs. So we will write the relative torsional displacement, theta 1 minus theta 2, the relative, and theta 2 is the deflection, is the rotation of the right disc. Left is theta 1. So simply, summation of momentum, there is only one momentum minus K equivalent multiply torsional stiffness, which multiplied by theta will give us torque or momentum. Theta 1 minus theta 2 relative angles, which is equal to minus K equivalent, sorry. J1 theta double dot 1. This is equal to summation of momentum for the mass around this axis. If I similarly write and plot the free body diagram for the right disc, if I just rotate toward clockwise, J2 theta double dot 2, again there is a rotational movement that contract this force, minus K effective or equivalent 2 minus 1 this time, theta 2 minus theta 1. So apply the Euler formula for the mass to summation of momentum at point O, J naught theta double dot 2. And summation of momentum is nothing but minus K equivalent theta 2 minus theta 1, which is equal to J2 theta dot 2. So let's call this equation 1, and let's call it equation 2. And this was the first step, right? First step, equation of motion, and second step, writing the equation of motion in matrix format. So we have to write equation of motion in a standard format. In a standard format, you need to write it and further simplify equations 1 and 2, J1 theta double dot 1 plus K equivalent theta 1 minus K equivalent theta 2 is equal to 0, and J2 theta double dot 2 plus K equivalent theta 2 minus K equivalent theta 1 is going to be 0. So I can easily transfer this equation of motion into a matrix format by the assumption of harmonic response for the theta 1 and theta 2, sine of omega t, and theta 2 would be capital theta 2 multiplied by sine of omega t. If I plug in here, I can construct my So this is for solving the matrix. So I just solve. This is for solving matrix equation. Here you need to go for matrix format. J1 0 0 J1 theta double dot 1 theta double dot 2 plus K equivalent minus K equivalent K minus K equivalent K equivalent theta 1 and theta 2, which is going to be 0 and 0. So these are symmetric. These two should be the same always. Symmetric with respect to the stiffness. And so for solving, for calculating the natural frequency, we need to make some assumption for the theta 1 and theta 2 as a harmonic response. So then you would be able to further simplify it like this. If you plug in, you can construct the matrix K minus M omega squared X or theta 0. Then K equivalent minus J1 omega squared minus K equivalent minus K equivalent minus J2 omega squared multiplied by amplitude of theta 1 and amplitude of theta 2. This is going to be 0 when our non-trivial response would be when the determinant of this matrix is 0. So solving determinant equal to 0 will give you the natural frequency. N1, omega N2. These steps are the same for all of the problems. So you know how to find the determinant of a matrix 2 by 2. Simply just multiplication of the 2, and so K equivalent minus J1 omega squared multiplied by K equivalent minus J2 omega squared minus K equivalent squared is going to be 0. So you need to further simplify it, and therefore you have to write K equivalent squared minus J2 omega squared K equivalent minus J omega squared K equivalent plus J1 J2 omega to the power 4 minus K equivalent would be 0. So you could easily cancel out this term by this term, and then for the sake of simplicity you would notice that there is the omega squared which is common between these three items terms, and you could simply factor out omega squared multiply at J1 J2 omega squared minus J1 plus J2 K effective is going to be 0. So therefore easily for this always for this type of system, one of the natural frequencies is going to be 0. So omega n1 is going to be 0 because this term can also be 0 and this term can also be 0. So if the right term be 0, then the second natural frequency would be square root of K effective or equivalent J1 plus J2 over J1 J2. So when one of the natural frequency of the system is 0, we call it semi-definite system. Semi-definite, like an airplane, like train. So one of the natural frequencies is 0 for this. So once you obtain the natural frequency, you could easily go for a step 3. So a step 3, this is natural frequency. A step 4 is mode shape, natural mode shape. So all you have to do is just go back, you have to come back and see this equation, the matrix, and always choose the first row or second row. So simply I will choose the first row and rewrite this. And by writing that, I will be able to come up with normal mode shape. So K equivalent minus J1 omega to the power 2 theta 1 minus K equivalent theta 2 is going to be 0. Before further going to solve the natural mode shape, let me calculate the second natural frequency. We already obtained the effective stiffness as 0.0365 10 to the power 6. J1 plus J2 is going to be 5 plus 3 over 5 multiplied by 3. The response would be 139 radian per second. So here, for the natural mode shape, you could easily find this ratio theta 1 by theta 2, which is going to be K equivalent minus J1 omega. So from this equation, you will reach to this equation. So in the numerator, we have K equivalent. So the first mode shape, you have to just insert the first natural frequency in the omega. So the first mode shape simply, so the first natural frequency is 0, omega is omega n, 1. So K minus 0 would be 1. So you can give a denominator 1, then you could say the first mode one. The second mode shape can be simply similarly obtained theta 1 over theta 2 at second natural frequency. Omega is omega n2 would be K effective minus J omega squared, J1, basically J1 omega squared, omega n squared. So K equivalent J1 plus J2 divided by J1, J2, which is going to, if you calculate, is going to be equal minus 0.5979. You have to simply give a denominator 1 here. Then you could say when theta 1, theta 2 the second mode shape would be 59799. You can come up with a geometrical interpretation for these two natural mode shape like this. For the first mode, theta 1, theta 2 is 1 radian. So if this one rotate 1 radian, these two rotate 1 radian, like this. So this is going to be, there's a solid system. So let's rotate like this. So you could simply show the first mode like this, 1 radian, 1 radian. However, for the second mode, if theta 2 rotate 1 radian, theta 1 will rotate minus 0.5979. You could show it like this. So the right will rotate, will like 1 radian. If the right disk rotate 1 radian, the other will rotate negative minus 5979. So this point is called node. You could identify at which place, at which point this node will be occurred. So simply you could call this length as L1, you could call this one as L2. We know that summation of the two, which is the value which is given to us at the first place. So we have, so for finding the node, identifying the node, we know summation of the two, which is given to us as L12 plus 16 inch. On the other hand, by taking advantage of a trigonomic function, trigonometric triangles, you could draw a conclusion that you could write L1 over L2 is, L1 over L2 is just the value, the ratio 0.5979 over 1. So these are also proportionate together. Since these are proportionate to this, therefore I could say this one will be proportionate by this side. Then by taking advantage of this relation, I can identify at which place the node will be occurred. So L1 is going to be 0.5979 L2. So you have two equations, you could easily identify L1 and L2. So we are simply done with first problem 5.7. Just let me know if you have any question, otherwise we will go for next problem as 5.9.
Yeah, just a small question. What
Yes.
once we found like the node and the two mud shapes, what are the real utility of this, like in our design? How can we? Is it like a critical design that we should avoid these frequencies, these mud shapes, or just trying to understand the significance of that?
Right. So yes, we have. For designing, we normally there is basically a excitation frequency, and these are omega n1 and omega n2. And for design point of view, we have to design, since if the operation of the system is given to us 112, we have to design in a way that to be far away from the, we have to keep natural frequency far away from the excitation frequency in order to dramatically reduce the amplitude. And once you turn off the system, there is no any choice. There is a huge vibration because one of the natural frequency is 0. So, but for the omega m2, you have to basically be far away from the omega n2 because if the omega, for example, if omega n2 is 95, so you cannot apply the external force reach to that. So you have to change the stiffness and this in order to make it lower like 35 to be far away from the excitation frequency in order to reduce the vibration. And for the node, just gives us the how this system will behave. So how they respond. So give us a view for other requirements, space and other things. So for 5.7 and 5.9, the next problem would be pendulum. Pendulum, you could take advantage of Lagrange, but this time I will solve it through second Newton's law, which is quite easy. And 5.9, it says, assuming a small amplitude, set up the differential equation of motion for the double pendulum using the coordinates shown in the figure and show that the natural frequencies of the system are given by the equation. So double pendulum. Mass 1 and mass 2. M1, M2, L, which is M1 is going to be equal to M2 like M. These are the same mass. And so this is given as X1, and this is also given X2, X1, X2, and this is going to be theta 1, and this is going to be theta 2. We have to set up equation of motion and show that the natural frequency would be square root of G over L 2 plus minus square root of 2. So, and also determine the ratio of X1 over X2 normal mode and locate the nodes for the two modes of vibration. So if I want to derive equation of motion, I can easily apply second Newton's law for linear motion, because if I assume for deriving equation of motion, we normally assume a very, very small motion. If I plot here, if you consider a very, very small motion, theta, I just magnify it for the sake of simplicity like this. I can relate linear rotational motion to a linear motion, which is simpler for me. So this is L, this is X1. And if I basically detach the second mass from the first mass, I can say for the second mass, I can easily apply for this one, I can easily apply second Newton of law, summation of forces at x direction is going to be mx double dot 1. So, and also I can similarly apply this equation of motion for the second mass, second pendulum. So here, for the second pendulum, if I draw a free body diagram, so there is a mg, and there is a basically the tension in the string. So T2. So the reaction of T2 will be applied in the first mass like this. So this is the problem of so the other session, Vincent asked me how we should choose type of method for deriving equation of motion. For this type of problem, and we have to find the reaction force between the different part of the system if we want to use the second Newton of law for deriving equation of motion when we are dealing with multi-degree of freedom system. Normally for this type of problem, which we have to take care of inner forces like this, Lagrange is much simpler. But now we have to use it because we have not reached to that method. We need to go for Newton law. So I can also easily apply the second Newton of law for the mass 2. I can say summation of forces apply to the mass 2 is mx double dot 2 at the x direction, just a linear motion for the x. Very simple. There is no any y motion, just x motion, right? Now I can so for this, if you consider the second mass, I can show you other forces. So this is a tangential line, and this is going to be theta 2. So for deriving equation of motion, I just started with this. Right hand side is very clear for me. So what for the left hand side, I need to know what kind of forces is going to apply for the second mass here, for example. So then I can easily write the equation of motion in the green line, x direction, x. So for this, there is a basically mg. So one of the mg term will come here, mg. If you project mg in the two, mg sine theta 2. And here would be mg cosine theta 2. And also okay, there is only one force, basically. So for, if take a look at here, this is a tangential direction, and this is a, and the green one is the linear, right? When the, basically when the theta is very small, as I show here, the two curves will be somehow will be in one direction, and we could say that at the x direction, so summation of f at x or at t direction is going to be mx double dot 2, which is going to be minus mg sine theta 2. So we know that if I come back here, we know how to easily relate x and theta. So here simply we have x1, and also I just magnify this theta 1 and theta 2. You know that this length x1 is simply L theta. This is L, and also this is x2. So x2 is x1 plus L multiply theta 2. This is x1. So x2 therefore would be x1 plus L theta 2. So you could easily substitute this x1 and x2 in the equation of motion, and then so here x2 is x1 plus L theta 2. Therefore x1 itself is L theta 1 plus L theta 2. So factor out L theta 1 plus theta 2, and you could take derivative from the both sides. X double dot 2 is L theta double dot 1 plus theta double dot 2. So simply the acceleration is obtained, and you have to plug in here, and the first equation of motion will be obtained for the mass 2. If you substitute, the first equation of motion would be simply m L theta double dot 1 plus theta double dot 2 plus m j theta 2. How I reach to this equation? You have to simply take advantage of a small deformation. For a small deformation, when theta is very low, sine of theta is approximately equal to theta. That's how I reach to this term, because mg sine theta 2 is more or less mg theta, and you see mg theta here in the right hand side. So this is the equation of motion for the second mass, and similarly we could go for mass 1, but for the mass 1 we need to obtain T2. So T2 from, if you take a look at here, T2 is equal to mg cosine theta 2, because I can write it here. So T2 is m2 g's cosine theta 2. M2 is mg cosine theta 2 is very small. That's why we could say is mg. Why? Because theta is very low, and summation, there is no any acceleration in the y or in the normal direction, my double dot. That's why there's you could consider as a static. T2 is m2g cosine theta 2. T2 we obtain as mg, then you could go for the first mass, which we draw here, first mass here. So you have T2, and then you could similarly write the equation of motion simply for linear motion. So first mass so T2, and there is a mg, m1g, which is mg, and so we have to draw tangential, and so I cannot continue this very fine update. I don't know why. So similarly, we could project T2 so my iPad is turned off. It's going to update. I don't know why. So similarly, you could you could apply the second Newton of law for the first math. Just project T2 in the normal and tangential direction, and apply the second Newton of law in the x direction. You will have T2.
Yeah, now it cut off.
So you will have T2 sine of theta 2 minus theta 1, and one term is mg sine theta 1, and you could so the first equation would be m l theta double dot 1. So I would like to give a 5-minute break, because I have to wait for this is going
No
to
problem. No problem. I have to go to the
start.
bathroom. No problem.
I will join with the iPad in the next 5 minutes.
Sure.
In order to start the drawing. So I cannot draw now. So I'll give you 5-minute break, 7-minute break, and
Perfect.
we will continue on. Now it's 5:09. We will start 5
15 something.
10 minutes.
Okay.
5:20 we will start.
Perfect. No problem. Thank you. No problem.
So let's go over this equation of motion for the mass one. Summation of forces is going to be mx double dot 1. x1 is L theta 1. X double dot 1 would be L theta 1 double dot. So in the tangential direction, so you have to project T2 in the tangential direction, and basically this is going to be continue of T1, and this is going to be theta 2 minus theta 1. So this T2 will be projected here like T2 sine of theta 2 minus theta 1, and there is a mg force also here, mg sine of theta 1. mg sine of theta 1, because this angle is still theta 1. So in the t direction, so this is on the t direction, summation of forces at t direction m x double dot t minus mg sine of theta 1 plus t2 sine of theta 2 minus theta 1 is going to be mx double dot t. X double dot t for mass 1 is going to be x double dot 1, which is going to be L theta double dot 1. So you could simply simplify. This is going to be minus mg theta 1 plus t2 theta 2 minus theta 1 m L theta double dot 1. So I can recap the two equations here. The two equations we obtained so far. Mass 1, m1 L theta double dot 1 plus 2 mg theta 1 minus mg theta 2 is going to be 0. And second equation of motion for the second mass is m2L theta double dot 1 plus theta double dot 2 plus m2 g theta 2 is going to be 0. Please note that m1 is equal to m2 is equal to m. So if you take a look at the question, we are asked basically to set up the equation of motion using the coordinate we are given is only x1 and x2. So we could simply transfer this equation and change any theta 1 and theta 2 in terms of, write them in terms of x1 and x2. So if I do that, I can simply, as I wrote there, x1 is L theta 1, x2 is L theta 1 plus theta 2. Therefore, theta 1 is x1 over L, and theta 2 is x2 minus x1 over L. So simply, if you substitute these two equations, you will have simply x double dot 1 plus 3g over L x1 minus g over L x2 is going to be 0. And second equation of motion, x double dot 2 plus g over L x2 minus g over L x1. So simply we could set up the matrix format, and I will not write the matrix, and just simply I will write the determinant matrix k minus m omega squared should be 0. So simply you will have 3 mg over L minus m omega squared minus mg over L minus mg over L mg over L minus m omega squared. Determinant should be 0. So this equation will give you the natural frequency of the system. So you have to multiply then 3 mg over L minus m omega squared mg over L minus m omega squared minus mg L over L squared is going to be 0. Therefore, if I further simplify it, I will have 3 mgl to the power 4 3 mgl m omega squared minus m omega squared mg over L plus m2 omega to the power 4 minus mgl squared is going to be 0. So as I told you previously, we are dealing with the equation with degree of 4. So if I further simplify it, I will have m2 omega to the power 4 minus 4 mg m squared omega squared plus 2. So here, in order to solve it, you could say alpha is equal to omega squared, and you are dealing basically with a quadratic equation, which can simply find alpha 1 as omega n1 squared is going to be g over L 2 minus, and then first natural frequency would be square root of g over L 2 minus square root of 2, and alpha 2 is omega n squared 2 is going to be g over L 2 plus square root of 2, which therefore the second natural frequency is going to be g over L 2 plus. If I want to write these two natural frequencies in a concise format, I will reach to the point the natural frequency of the system is as g over L 2 plus minus square root of 2, which we were supposed to reach to this point as it is given in the question. So we are done with basically the natural frequency, and the second part is natural mode shape. So natural mode shape, so use one of the two equations of, use the first row of the matrix format equation and put the natural frequency in that equation. Therefore, the first, if I insert and substitute the first natural frequency in the first row of the matrix format of equation of motion, I have 0.414, and second mode shape x1 over x2 would be minus 2.414. In order to geometrically interpret the normal mode, all you have to do is just giving a denominator of 1. So x1 over x2 is 0.414, just 1 here, and x1 over x2, second mode shape is minus 2. For the first mode, it can be translated as if the second mass displaced as 1 millimeter, for example. If the second mass displaced as 1 millimeter, 1 unit, the first mass is going to be displaced by 0.414 millimeter. The first mode operation, but the second mode of operation, it can be translated as if the second mass displaced as 1 millimeter, the first mass is going to displace as negative. So here, like, so the second mode shape would be like this. So minus 2.4, for example, millimeter. So there is a note here for the second mode shape. You could locate the node. So here, basically, this is L and this is L. You could call this length as A1, and you could call this unit, this length as A2. So minus 2 is length of this side. So A1, therefore, over A2 proportionate would be proportionate as the absolute value, basically 2.414 over 1. On the other hand, we know that A1 plus A2 is L. L is given to us. You could simply identify the node. Therefore, A1 is going to be 0.293 L, and A2 would be 0.707 L. So all you have to do is just substitute either A1 or A2 by one of the two relations. So A1 is going to be 0. If you calculate, would be like this. So you just substitute A1 here, and you will solve the equation for A2, and you will find A2 summation of the two is L. You could easily find A1. So this is how we, so as you ask me what one of the other interpretation, there is a point basically at the node that the displacement is 0. And there would be, at a specific time, there would be no displacement. This is a property of the node. So this is how basically we solve this type of question. If you use Lagrange, you will set up the equation of motion using Lagrange, and the rest would be the same. As soon as you reach equation of motion using Lagrange or Newton law, and then you have to transfer into the matrix format and then assume harmonic motion for the response, and then solving the determinant matrix, and you have to go for finding first and second natural frequency. If three system, you have to find the three, but generally we are dealing with the two masses because the determinant of the 3 by 3 matrix is very difficult. It's quite difficult. And then you will go for natural mode shape. Basically, now we are finished with question 5.9, which I was supposed to give you hint, but I rather prefer to solve it. And 5.20 would be another question. Before going to that, just let me know if you have any question, and I can explain it to you.
No problem. I don't have any question.
Okay, 5.20, the next problem. It says choose coordinate x for the displacement. So let me plot firstly. So there is a beam which is attached K. From the right side, another spring attached at the end of the beam K. The center of gravity is here, C. This is L over 2. This is L over 4, and this is L over 4. So, and JSC is given basically mass moment of inertia 1 over 12 ml squared is given to you, and m is mass of this beam. So choose coordinates x for the displacement of c and theta clockwise for the rotation of the uniform bar shown here, and determine natural frequency and mode shape. So how we could determine natural frequency and mode shape? We have to basically derive equation of motion. So simply there is as soon as you attach this uniform bond to the spring, there is a static equilibrium position, a static deflection, and then so this uniform bar can independently move upward and downward, and at the same time can independently rotate. So that's why we could draw a conclusion that this uniform bar has, this system basically has 2 degrees of freedom system, has 2 independent motion, one vertical motion and the other is rotational, which are basically independent from each other. So we are asked basically to consider a clockwise theta, and so you could easily take advantage of second Newton's law for linear and rotational motion. So here basically there is a static equilibrium position as soon as you attach static. So from this point, in order to derive equation of motion, I simply pull down like this the beam, the C from here as X. So X, and then I can rotate like this. Rotate the system like this, and then the left spring will oppose the motion. The right spring also will oppose the motion. So basically the left spring is located here. Negative. So, and also the right spring will opposes the motion. The deflection which is applied for the right spring is this length, x2, and the deflection for the left spring is this length, basically. So therefore, this length here, if I magnify, this length is, this is theta, right? So this is going to be L over theta, L over 4 multiplied by theta, because this length is L over 4. And also the deflection at the right spring is x plus this deflection, which is going to be half L multiplied by theta, because this is half L and this is theta. So this is going to be total deflection for the right spring, which is equal to x plus L over 2 theta. Therefore, you could say the spring force in the right, for the right spring, the force is going to be K x plus L over 2 theta. Similarly, the spring force which opposes this motion is going to be x. So this deflection, we have to relate from this point which we start the motion, right? So it's going to be x minus L over 4 theta. So here the total is x. So based on our coordinate, at first step we have to, at a static equilibrium position, we have to measure the displacement for the spring, for the left spring. So the total deflection is x minus L over 4 theta. So we have linear independent motion and we have rotational independent motion. At first, go for linear independent motion. So summation of forces applied at x direction. Our vertical motion, suppose is x direction, is going to be mx double dot, right? X is just displacement for x point C. This is our assumption, right? The positive direction is in the downward. We always displace the system in the positive direction, which we are assuming for the sake of simplicity. So therefore, I have two opposite motion, the left spring force minus K x minus L over 4 theta minus K x plus L over 2 theta is going to be mx double dot. This is my first equation of motion, and just go for independent rotational motion. Summation of momentum around point O would be mass moment of inertia around point O, theta double dot. So point O here basically is JC. The system is rotated around the center of gravity. And the positive direction, as the question also is giving us a hint, is clockwise, basically. Clockwise is our positive. So these two, the right spring, if you take a look at here, the right spring will create counterclockwise momentum. On the other hand, left spring will create clockwise momentum. And these are basically the arm associated for each force which create momentum around point of C. Therefore, I can easily write the corresponding momentum. So for the left spring will create clockwise momentum. So K x minus L over 4 theta. This is force multiplied by the related arm L over 4, force arm, torque or momentum. However, the right spring will create counterclockwise momentum, minus K x plus L over 2 theta multiplied by the related arm, which is L over 2. Force arm and torque or momentum is going to be equal J C theta double dot. Therefore, the next step is just transferring these two equations in the matrix format. So for the linear motion, I have mx double dot plus 2kx plus k L over 4 theta is going to 0 from the left. From the rotational motion, j theta double dot jc plus k L over 4 x plus 5k over 16 L theta is going to 0. Therefore, m00j x double dot theta double dot plus 2k kl over 4 kl over 4 symmetric 5 over 16 kl squared x theta is going to be 0. So these are statically coupled because at each row we have x and x2. So these two always the same, just symmetric, and dynamically uncoupled. If this one of the 0 is not 0, it was a number, we could say it is also dynamically coupled. It means at each row we have x double dot 1, x double dot 2. So dynamically uncoupled and statically coupled. So for natural frequency, you have to assume a harmonic motion, x double dot 1 minus omega squared x sine of omega t, and theta double dot is going to be minus omega squared theta amplitude sine of omega t. And then you will reach to this point 2 minus 2k minus m omega squared k L over 4 k L over 4 and 5 over 16k L squared minus j omega squared multiplied by x theta is going to be 0. So therefore, the determinant of this metric should be 0 in order to satisfy this equation. Then 2k minus m omega squared. So for the natural frequency,
The determinant, right? Equal to 0.
yes, determinant equal to 0 mj omega to the power 4 2kj 5 over 16k L squared m omega squared plus 10 over 16 k L squared k squared L squared 16 equal to 0. Then simply, if you simplify and use sum of modification, and you have to apply j as, you have to insert j as m L squared 12, which is given to you, then you could further simplify it like this. Omega to the power 4 minus 23 over 4k over m omega squared plus 27 over k over m squared equal to 0. Therefore, the natural frequency would be, could say omega squared is lambda. Lambda 1 is omega n1 squared 1.645. Therefore, the first natural frequency is going to be 1.2826 k over m. Lambda 2 is omega n is 2 squared is going to be 4.105. Therefore, the second natural frequency would be square root of this number, which is going to be 2.026 square root of k over m. So we are done with the two natural frequency. For natural mode shape, all you have to do is just take one row of this equation, this row, and just read it. Read this line and write it here. X over theta is going to be KL over 4m omega squared minus 2k, which is going to be so can you turn off the microphone? There's a noise here. Thank you. So if you plug in the first mode shape, it's going to be minus 0.74 L. You have to give a denominator of 1. The first and the second mode shape would be 0.1187 multiplied by L. It is better give a denominator of 1. So the rest is easy. So we just come up with basically natural frequency and mode shape. So you could write it like this. It's okay. You could say x theta 1. If there is a 1 radian rotation, there would be minus 7 point L and x theta 2. If there is a 1 radian rotation, positive 1187 L. So these are so positive. So here, this point will go here. Basically, positive movement and positive rotation. Rotation 1 radian, and the length is given 0. On the other hand, for this case, if the static equilibrium position is there, black line, and then for the second mode shape, again, there is a clockwise motion. However, sorry, here it should be like negative. It's correct. 1 radian. 1 radian rotation. There is a negative displacement at point C, minus 0.7, which is function of L. So these are the natural frequency and natural mode shape. And in the next session, we are going to basically finish chapter 5 on Monday, and on Wednesday we will start Lagrange. So next session I'm gonna finish. So I think this is enough for today, and we will finish the chapter 5 in the next session. Just let me know if you have any question.
Very good. Thank you very much.
You're welcome.
Have a good day.
Have a good day. Thank you.